wanted to pick up our discussion of a driven damped harmonic oscillator and looking in particular at the resonance width that we had talked about in class on Wednesday, and just have a few more thoughts I wanted to share with you. So if you remember on Wednesday, we looked a lot at these sorts of line shapes where this is plotting a squared on the y-axis, which we said is proportional to the energy that got put into the oscillator by our driving force, and this x-axis here is the frequency of our driving force. So if we have a low frequency, we're not going to excite it much. If our frequency is too high, we won't excite it much. But right on resonance, we get a huge response. And so it's important to characterize the width of this resonance to understand how precise our frequency needs to be in order to excite it. So this function here is a Lorentzian. It gives us a resonance behavior, and a squared is given by this function there. We could take a derivative with respect to 0. In particular, we took a derivative of the denominator, and so to minimize this denominator in order to maximize a squared. And using that, we got that our resonance frequency is the square root of omega naught squared minus 2 beta squared. We can plug this value in to our expression for a squared, just plugging in this for omega, and we get that the max amplitude squared is this function here. It gets simpler if we assume that beta is much less than omega naught, so we can neglect this term. And so we get that the amplitude here is f naught squared over 4 beta squared omega naught squared. So we made this assumption that omega naught is is much greater than beta, or beta is small, so that we have small linear damping. The damping frequency is much smaller than the natural frequency of our oscillator. So that means that our resonance frequency is basically omega naught. So we can assume that we're at omega naught here. So then the question is, what is the resonance frequency? Sorry, the resonance full width at half max. What's the width of this resonance here? So to calculate this, we're going to determine the frequency values of our a squared. So at what values of omega is a squared equal to half the amplitude, right? So on this side we have omega minus, this side we have omega plus. For both of those values of omega, we should get an a squared value that's half of our maximum. So that's what this is expressing. So if we plug that in, so here's our a squared max over 2, so that's just from our a squared max here, divided by 2. And then here's our expression for a. So here's our starting point, and I think this is kind of where we didn't know where to carry on from here when we were in class. So the key is that this expression on this side, we've already assumed that beta is small, that the damping frequency is much smaller than omega naught. So we need to make the same assumption on this side over here. We can't make any simplifications here for omega because we're subtracting omega squared from omega naught squared. So even if omega is really close to omega naught, the value inside the parentheses here that's getting squared is still going to depend a lot on small differences from omega naught. So we need to keep the full omega here. This value here, we can do something different. We know that we're looking at 4 beta squared omega squared, and we're looking very close to the resonance frequency. And since beta is small, remember we said that the resonance frequency is square root of omega naught squared minus 2 beta squared. Beta is very small. The resonance frequency is basically omega naught. So we can say that for the omega values we're looking at here, this omega value here can actually be approximated as omega naught. So at that point, from this point on, it's basically just algebra. So you can cancel some terms, and you get to an expression for omega minus and omega plus is equal to omega naught times the square root of 1 minus or plus 2 beta over omega naught. So you could leave it here and say that that's our answer. But this isn't very intuitive. It's the square root of these two terms combined together. So we can again realize that we're looking for small values of beta compared to omega naught. So that means that this second term here under the square root is going to be pretty small. So we need to Taylor expand the square root of 1 plus or minus delta for small values of delta. And so you should be able to do this Taylor expansion backwards and forwards and in your sleep and on your head. So square root of 1 plus or minus delta is approximately 1 plus or minus 1/2 delta. So if we use that, delta is 2 beta over omega naught. We get omega minus or plus is omega naught minus beta for omega minus, or omega naught plus beta for omega plus. So that gives our full width at half max is omega plus minus omega minus is 2 beta. So that means that on this curve, the full width at half max here is just 2 times beta. So the linear damping is directly connected to how wide our peak is.